so let's get started. It's great to have Sookhyun Lee here, who got her PhD from Stony Brook working with Abe Deshpande. She spent a couple of years as a research engineer at Samsung before coming back and seeing the beauty of academia, and is now a postdoc at University of Michigan, University of Tennessee, working on LHCb and FP. So, anyways.
Thank you for the introduction. So my research area is quantum chromodynamics on closed QCD sites. So I focus on the structure of the proton and how the hadrons are formed. And so this is the outline of my talk. So I will go over the properties of QCD and lay out a few concepts that are relevant to my research. And then there are two main parts where I will discuss in detail I will prove the proton structure and hadron formation. And then lastly, I will discuss future directions based on what we have learned and what we still don't know. So as we all know, today, the visible matter accounts for only 5% of the energy of the universe, and 95% of the visible matter is made up of baryon matters. So the protons and the neutrons, the building blocks of the visible matter, they themselves are not elementary particles. And so then what are they? What are the elementary particles then that make up the visible matter? There are 6 quarks and 6 leptons in the standard model of the particle physics with the 4 force carriers. The standard model only includes 3 of the 4 fundamental interactions. The first 2, as you're familiar with, electromagnetic, mediated by photons, and weak, mediated by C and W bosons. Those are unified as a electroweak theory in the 70s, and the strong force is what the main focus of my research is. The gravitational force is not included in the standard model, not because it's not important, but because we don't know a theory that can unify all of them. And in fact, gravitational interaction is the most important way to interact with the dark matter. So now, if we look at the history of the universe, after the Big Bang, the universe went through a few transitional periods. The important ones are the electroweak transition, where the electric force and the electromagnetic force and the weak force split, and followed by QCD transition, where the neutrons are formed. If you look at the here, the particle energy of the accelerator around these transitional periods, because that's what we want to explore. And so, what is QCD? QCD is a quantum gauge field theory of strong interaction between quarks and gluons, collectively called partons. One key important property of the gluons, the force carrier, is that they carry color charges. So hence quantum chromodynamics. And so and additionally they as a result they self-interact, and as a result there is this phenomena called asymptotic freedom. And what it means is that when the partons are at a very short distance, say less than 10 Fermi, they behave as if they are free particles. And so that's because when a parton gets very close to the other parton, it sees less and less color charges carried by the virtual gluons that are created around that parton that you're getting close to. And so your the strong coupling, effective strong coupling constant, and the strength of the interaction becomes smaller. And the existence of this regime, the asymptotic free regime, enabled perturbative calculations of various hard scattering processes, and that led to the success of the QCD. Now, if we go to the other end, the confinement you see, if the partons are pulled apart at a long distance, what happens is that unlike the QED case where the photons do not self-interact and the force will fall off as one of the R square, as you all know, in QCD, more and more gluons will be created, squeezing into the lines of forces, and then it becomes the potential becomes linear and behaves as if a string. So how strong the spring constant is for the nuclear force is that it's equivalent to it's equivalent to gaining energy by lifting a 16-ton truck. And so as a result, what we see is that the quarks and the gluons can never be isolated or directly observed. So we've discussed the two key components, two opposite ends of what happens in QCD. Now, how do we incorporate these two concepts into QCD to make predictions for the measurements of experiments? Is that I'll give you an example. You have two protons colliding with each other at very high energy. They break up and go through photonic scattering, and eventually generating at least one Hadrons at the end. So the probability of this event happening is recorded in the scattering factor measure is expressed as a convolution of non-perturbative functions at long distance and the hard scattering cross-section at short distance. So at the initial state and the final state, the hadrons are in a confined state because it's long distance. So how we describe them is that it can be expressed as a function. The probability of finding a certain type of parton inside a proton can be defined as a function of the fraction x of the proton momentum carried by the parton. In a similar way, finding a hadron inside a parton, certain type of parton, at the end, at the final state, is defined in terms of Relativistic functions. So this factorization, when combined with the universality of these non-perturbative functions, is a powerful tool that can provide predictive power for physical processes and variables across the different collision systems. So speaking of different collision systems, what are the colliders that there are in the world? The first type is Electron Collider, most commonly colliding electrons and positrons, found in Japan, KB, and in Switzerland, and Japan. So thanks to the structuralist electron scattering, these provide the most precise information about the fragmentation functions. Here I show the 3Z event display with very clean signal. It corresponds to the diagram above, where you have quark and antiquark created and accompanied by a gluon radiation. So the other type of colliders, electron hadron or electron-ion collider, most notably HERA and future EIC. And so these are the best tools to study probe the proton structure because of the fully known electroweak interaction between the bosons and the nuclear. So here I show the neutral current deep inelastic scattering, where the gamma is neutral bosons are probing the inner structure of the proton. Now, the third type of detector of the colliders is a Hadron Collider. A lot of you are familiar with the LHC, Hadron Collider, and relativistic Hadron-Ion Collider, and Electron, and so on. So these are good test ground for various components of QCD and beyond. And so now I come to the second part of my talk, where I will be discussing the structure of the proton in terms of their properties. So I will start with the momentum component. So the collinear structure of the proton has been studied for the past 5 decades. And it's here I show this most up-to-date understanding of the structure of the collinear momentum structure of the proton from the state-of-the-art QCD analysis. I will get back to it in a moment. So let's go back and see historically how we come to that point. So early parton model, the sun rules were very simple in its form. To start with the very simple constraint, the balanced quark number defined as the difference between U quark and U bar for PDF integrated over possible and momentum fraction has to be 2, and similarly for V quarks it has to be 1. But at the experiments, you don't have access to individual core PDF information. What they do is they have to do different experiments and infer the information. So this is an example where you measure the structure function in neutrino and anti-neutrino scattering, and then average over them, and you will have this the barium number sum. So, and then you can combine these with other experimental results and to get the individual PDF information. Another example is momentum sum rule. The gluons, their momentum cannot be measured. So you have to rely on the momentum sum rule to influence their contribution to the proton momentum. And so, as we know, this is too naive a model to describe all the existing data in the world. And what the people had to make modifications to the model, and one of the most important things is that the PDF depends on the hardness of the scattering, expressed as Q squared, and also C quarks and gluons contribute have sizable contributions to the structure. So how did they measure actually the parton distribution functions for quarks and gluons? Is guessed and the legend of the previous plot. The global analysis that they did used mostly the data coming from HERA. HERA is so far the first and only EP collider. It's hosted by DESI in Hamburg, Germany. They had 2 experiments, one on the north, H1, and one in the south, the Cs. And they had 2 periods where the first HERA 1 period, they had unpolarized electrons, and the HERA 2, they also had polarized. The energy of the center of energy was 310 GeV. Is comparatively high when you compare that with 200 GeV, 500 GeV for Chabatron at 1 TeV or 13, 14 TeV at LHC. And so now that's how they extracted the collinear momentum distribution. the header. So now, I want to discuss the spin part of the proton structure. The polarized protons we first studied in the 80s, but how the decomposition of the angular momentum is done is still being actively investigated. So going back to the parton model, in the 80s, people used to believe that the spin of the proton came solely from the balance force UD. And then there was this data that published by EMC that showed striking results that the core contribution to the proton spin was at best 30%, which is also this discrepancy is also shown in the measured Q1 structure function as compared to this parton model predictions. And here, introduce this polarized parton distribution function. Sometimes it's called the helicity parton distribution function. Is defined as the difference between two different helicity states. So we're gonna see this a lot in the following slides. So this really shocked the community, and there was this famous paper proclaiming there was a crisis in the proton spin. So people started looking at elsewhere, in particular relativistic Hadron-Ion Collider. The RIC is the world's only polarized synchrotron collider with the capabilities of accelerating protons to light and heavy ions located in Brookhaven, Long Island, New York. The protons can be polarized longitudinally as well as transversely. That actually led to success of the spin program for the classic quantum. So recently there are two long experiments. One is to I've worked on Phoenix. Now it's been replaced by S-Phoenix, and expecting first run in May, and to start on the and so in RIG, we can have a direct access to the helicity gluon distribution functions at leading order. This is in contrast to DISS measurements, where gluon comes in at the next leading order, so you have to rely on the dependence of the hardness of the scaffold, which is shown as the Q dependence. And so the reason why we're more sensitive directly to the delta G is because the kinematics for jet and Hadron productions are dominated by glue or pork glue parton scaffold. So you can access this information by measuring longitudinal double spin asymmetry. And this asymmetry is defined in such a way that it's proportional to the production rate for the like sign versus opposite sign proton time series. So both protons are longitudinally polarized, and measuring the production asymmetry. And so we've also, these here I show the results from jets and neutral ions from with high statistics. With Phoenix also measured charged ions, which is more precise. The first measurement that I've done had hinted that there is non-zero polarization with limited statistical power. And additionally, it showed that the ion productions are shown to be consistent with the predictions that were made using the data from other experiments and collision systems. So this highlights the universality of the non-perturbative collinear PDFs and fermentation functions, and the success of collinear vectorization of the perturbative GCD. Now, the precision measurements from STAR and WIC were used to perform a global analysis of the world data, and it demonstrated high impact on constraining the G, especially at X range greater than 0.05. And the analyses were performed by two independent groups, and they both were showing that the contribution to the proton spin could be somewhere around 35 to 40%, which is really surprising. And so this is how we see proton spin today. The intrinsic contribution from the spin of the partons make up 60%, very roughly. It has a large uncertainties. The rest may come from protonic motion. But at EIC, we would be able to drastically decrease the uncertainties on this special delta G by going to being able to go to very low X, where we don't have access with current experiments. So now another major program from the WIC was to look at the C quarks, how they are polarized, and if there's any flavor dependence. So I'm looking at the spin and flavor components of the proton. And so for this subject, W production is advantageous because the electroweak interaction does not conserve parity. So when you conserve the parity, it means that you have a mirror symmetry. So in fact, W production maximally violates parity. So when you have one parton, say left-handed quark, the other parton has to be right-handed anti-quarks in different flavor, and that gives a sensitivity to the flavor separate polarized secret distribution by measuring this longitudinal single spin asymmetry. The longitudinal single spin asymmetry is defined by the general symmetry between the positive and negative Hadron. Here, you only have one polarized longitudinally. So STAR measured the W asymmetries, and the impact shown in the shaded band showed clear evidence of flavor asymmetry in the polarized C. You see that here the uncertainty is really small to say safe enough to say that there's asymmetry in the polarized C. And Phoenix also measured the same asymmetry, and we've seen consistent results, and we also extended the tuner range. And so this was the C program, W program that we've done. And now I'm going to discuss the interplay between the momentum and spin. And this way we can probe really intricate structure of the proton. So to give you an answer right away, what we can learn from it is we could probe the three-dimensional structure from simple collinear parton picture. So there are several ways to probe the transverse structure of the proton. I'm going to discuss this two approaches with the check marks. Because it's what I mostly worked on. And so here I show a set of experimental data that was really puzzling for a long time. What they measured was asymmetrical transverse single spin asymmetry. So you have one proton transversely polarized, and you're measuring the production asymmetry. between up and down, and if you rotate the reference frame, it becomes left and right, left-right asymmetry. The naive PQCD prediction, including parton model, told us that it will be suppressed by quark mass divided by the Howard scale. But what we saw was that the asymmetry actually rises as you go closer to the direction, the forward direction. And so there were two approaches to solve this problem. One is they propose that the asymmetry can come from non-perturbative dynamics, the quantum interference between one active parton and two active partons interactions. And so I showed this one example of QZQ correlator when I showed the one parton interactions. So in this solution, it's kind of an extension from the collinear. Normally you would have a twisted tube, so you would have this one. You would not need another scale other than the Howard scale. In the second approach, you have a twist two TMD approach. You're explicitly introducing transverse momentum component in your PDF. So in this case, you would need two scales. The one example is the Sievert's function. Sievert's function can account for the velocities coming from the spin of the nucleon and the momentum of the parton, the intrinsic partonic motion. So that's the two approaches. I will go over a few experimental measurements that could be explained or explored by the two approaches that I show. The forward means coming going closer to the beam direction. So I have a slew of the measurements using neutral measures. You see the similar rising pattern. The theoretical analysis told us that there is more final state effects than the initial state effects, but the study is still ongoing. And now, if we focus on the direction perpendicular to the beam direction, so the rapidity, we've measured this. And we focus on the direct measurements on the right because this is, this would allow us to probe the triangle correlator. The triangle correlator is another type of twist correlator. You can replace the quarks in the QGQ correlator with the gluons. So it's another surviving kind of non-perturbative function. And so because the direct photon production is sensitive to the gluon initial state gluon, this was supposed to be sensitive to the driving correlation, and we actually demonstrated that it's possible to discriminate against different models and constrain this non-perturbative object in this paper published by Phoenix that I was also involved in. And so apologies for too many plots. So this is the last of the Phoenix plots that I want to just say that there was another open eddy flavor measurements that we performed at a mid rapidity that was supposed to be sensitive to triangle correlation because the process are dominantly fluid fusion process, and we've done the first analysis try to constrain where they are. It's very oversimplified analysis. It indicated that we do not yet see sizable contribution coming from triangle correlator, but it's we've measured it. So I've talked about the measurements
from the first approach. It's just kind of like extension from collinear 2. We're going to add, you're adding more field and collinear 3. Now I'm going to discuss a few measurements making use of this scale hierarchy, where you have in this TMD approach, you need a soft and hard scale, and that the LHC would give you that energy hierarchy. So you would, in particular, Drell-Yan process is really interesting because the photon here coming out with this PP collision would carry information about the transverse motion inside the photons. So 3 of the 4 LHC experiments measured it, and they've done the groups have done some analysis, and this is how we see the unpolarized TMD transverse momentum dependent parton distribution function inside the proton. So now still on discussing the Drell-Yan. So Drell-Yan process, you have to boson that decays into dimuon decays, and it has some angular distributions, and you have angular coefficients. And particularly interesting is the A2, which carries information about this quark spin momentum correlation. And the LHCb very recently measured A2, and there's a slight hint that there's some non-zero contribution, not non-zero quark spin momentum correlation effects. Now, so I've discussed the 2 approaches and some measurements. There is also a theory that showed that when the soft part of the soft scale becomes larger and larger and it becomes comparable to the higher scale, the theory can be unified. And this opens up new opportunities, especially in PIC, to expand and test the complicated QCD framework. We can test the evolution, universality, and the factorization hold and stuff. There's a lot of interesting stuff that can be done at the IC. Okay, so this is the 3rd part of my talk, where I want to discuss the Hadron formation, which is most poorly understood compared to other parts. So to tackle the hard problem, we need to make use of all the available tools and ask right questions. So I think that one of the most promising tools is using jet and jet substructure. A jet is a collimated array of particles that are coming from hard parton. So the jet, you can think of jet as a whole, you can think of like a hard parton, and it's a proxy for hard parton. And so because we don't understand theoretically from first principle on how the hadrons are formed, there are some models available, and those are implemented in modern multi-hour simulations. These 2 are the most successful ones: the string model and cluster model. So if you remember at the beginning, I talked about how the confinement at long distance, the nuclear force acts as a string, right? So you kind of have the quark and anti-quark oscillating, and then it has it gets pulled apart and it builds up potential energy, and at one point it will break up and create another pair, and it keeps going, and eventually nearby partons will form a co-neutral hadrons. That's how they implement it. The cluster model is a little different. You have a shower process, but the shower process already pre-confines the pre-confines before the highly excited hadron states, also called as clusters, form. So they have their own strength and weakness. You can, they have also a lot of parameters. So when you see results from our experiments, experimental analysis, you will see a lot of times comparing to Wikipedia, and so I just thought that I would introduce what it had. So that was a qualitative description, and I apologize again for a lot of symbols, but I promise I will focus on the transverse momentum dependent fragmentation function. It's a probability density for finding color neutral particles inside the envelopes partons. So I'm going to show this as an example of how jet substructure can be used as a tool to extract information in a clean manner. So I'll also compare or discuss the previous more traditional way, how they have the limitations and how we can overcome it. So the examples are plus E minus and semi-inclusive and photon Hadron collider. Just here showing as a first example more traditional way, but this is more recent measurements that they measure the production rate as a function of the energy fraction carried by the Hadron and the transverse momentum, and the measure that is for like how collimated the events are. So this is sufficiently differential measurements, but there's no, it's non-trivial to associate the Hadrons to the initial partons in a clean way. And this is the second example, semi-inclusive DI. It's a kind of DIS, deterministic scattering, but you have one Hadrons at the end. This kind of measurement is limited by due to the ambiguity by transverse momenta of two Hadrons involved instead of one, so that it's less direct measurement. So if you transverse momentum gets contribution from the initial parton and the final state Hadrons, so that kind of is less direct measurements. So if you use jet substructure, you could do the clean measurement, which goes straight to it. So if you measure jets at very high energy without looking at the structure, you can perturbatively calculate it because it's a proxy for the parton. If you measure a Hadron instead, you would need a fragmentation function, which is non-perturbative function. If you want to look at the structure inside the jet, it will tell you a lot of things. And this, there has been theoretical advancement that enable to calculate these substructure observables, and these observables are all at different scales. So by measuring multiple observables, you will kind of probing multi-scale of the energy. So I'll give you show an example of the lightning initiated jets, how they fragment into Hadrons. So what we measured at LHCb was that we measured the charge Hadron distributions inside the jet in association with the sea boson, because of the Compton QCD is the dominant process. Your jet would be predominantly coming from light quarks. And here in this formulation, when you measure the longitudinal momentum profile as well as the transverse momentum, you would be able to access the traditional TMDPDF. So here we published one-dimensional results, the ZGP, the neutrino profile, and transverse momentum, and the radius with respect to the jet axis. This is still not give us full picture because we haven't measured the Z and J simultaneously. If you do that, you could learn a lot of interesting correlations and how they behave is surprising. So this is the first transverse momentum dependent jet fragmentation function for all charged ions. So you see this correlation between the longitudinal and transverse dimension, and also like higher harder jets are they produce more soft particles and they tend to be wider. And for a given momentum, collinear momentum fraction, when you have harder jet, your transverse momentum gets also larger, which is consistent with the Markov chain fragmentation models, which are implemented in string clustering models. We've also compared that with the lower energy. So the previous one was 13, and this the one-dimensional one was 18 ATV. So you see the signal pattern. Yes, you have this complex structure where you have this the region where you are sensitive to color coherence, and you also have this scaling behavior region, and also the higher energy produces more soft particles. It's kind of consistent in the picture. And we've also measured the jet fragmentation function for identified particles, and here you can see that the mass dependence and the flavor dependence of pions are the most dominant one because of the valence content of the proton, and there's also mass effects where protons and kaons are heavier particles tend to start at a larger threshold C, and there's this interesting behavior between protons and kaons that really release GT jet. And so we've also did the same analysis with the multidimensional analysis for identified charged ions. You can see this nice just 3D distributions that clearly show that the heavier particles takes the more fraction of the initiating parton. So I'm gonna talk a little bit about the charmonium. I worked on this. So you have the charmonium is a quark and anti-quark bound state, and because they are heavy quarks, the theoretical description is a little different from very different from light quark mesons. So there has been some models that attempted to explain the polarization and production, but the most successful and robust one was non-relativistic QCD, because they're heavier and they're non-relativistic, so they use a different framework. But then NRQCD still cannot describe the production and polarization at the same time. This is the paper we published using the Phoenix data. You can see that the NRQCD predicts higher polarization, but you do not see any indication. And we also learned that there is for the production rate, there is a logarithmic dependence on the center of beam energy. So, and this is another plot that kind of summarizes that none of the other experiments see the size of the polarization that the NRQCD predicts, and we really need new approaches. One of the approaches that involves jets, of course, is the charmonium jet. LSCB measured the collinear jet fragmentation function Z here, and then it was surprising at first because it was so different from the PTF prediction, and it turns out that the PTF doesn't really implement this gluon to ceremony and fragmentation dominance in the simulation. So when they use the right fraction, it was consistent, but then you kind of didn't learn anything. So we are really in need of new approaches to test QCD, and I have some ideas to further study. And so, what do we still not know? These are the questions that I would like to pursue answering in the next phase of my career. So how does the perturbative to non-perturbative transition occur in Hadron formation? I think if you really make use of the jet substructure and high energy at LHC, or use the energy hierarchy, we could learn a lot of things about this question. And are the effects of hadronization universal between different collision systems? I think it will have to involve different colliders, types of colliders, and in the near future, I also want to research on this, what are the implications of current findings in extreme environments such as EA. And so the last one is kind of from the previous page, working further measurements using jet substructure technique to teach us on the photon production mechanisms. So
I think you've got 5 minutes left.
okay. So the key component to answer one of those questions is using the EIC. In fact, I initiating a program that could be done at EIC while I was involved in the detector requirement studies for the EIC. So the at EIC, for the first time, both electrons and protons are polarized. At Terra, only the electrons were polarized, but this time both are polarized. And at the center of mass energy can go up to 140 GeV and very high ambitious polarization. And the finalizing the detector design is underway. That is fundamental questions that people are trying to answer. I'm really excited about the prospects of the EIC. So what we are trying to do is it's a multi-pass study, and one aspect is it's a precision measurement of one of the most important parameters in the QCD, strong confidence constant alpha S. So motivation is that the people have done some event change measurements at E + E-, and they saw relatively large deviation from the rest of the data, and so it kind of motivates us to study event shapes in EP collisions. And the other motivation is that so Hera is an EP collider. They can do really good jet measurements, which is kind of related to event shapes, because when event shape includes the jet, so we kind of show how it tells you how jetty the events are. So now, currently the theory uncertainty dominates, but we will soon have NPA accuracy summation possible, which will be really beneficial to the other components of the event shape measurements. So I'll just introduce one of the examples of event shape event shape observable. There's one jetting. It's a global, and you're looking at the entire event, and it's a Lorentz invariant and input and so on. It's sensitive to strong coupling constant as well as PDFs, which are the most important ingredients to make precise prediction for any kind of experimental measurements. So it has a high impact, And the current, at the precision that the theorists are working on are expecting that we are going to be sensitive at 1% level to constraint in alpha S. So the analysis is underway. It's when you measure more differentially, you could see this beautiful patterns like where the the events are more collimated. So 0 is like tensor-like events, and 1 is a lot of soft-jet events. So the dependence is very interesting. And what I'm really interested in, that actually got me interested in this project was, if you look at the shift between the parton level and the Hadron level, that's kind of sensitive to the hadronization effect. And if you measure that, there are many ways to define the observers that make it sensitive to the self effects. And you're gonna have like multiple objects for each collision system, and you have it in different systems, and you can actually test. And it also helps the theory to become more robust, because you are measuring the same object in different systems, and you have to make it consistent, and so on. So this is one of my interests that I'm really passionate about. So I think I finished in time. So this kind of summary, the spin the spin structure, and there's gluon polarization and substructure. There is this asymmetry in secret polarization. We've seen the transverse structure. We can actually see different spin momentum correlations, and also we're looking forward to working with the jet community and using jet substructure. And finally, the EIC that often me training to further test and advance our understanding of QCD, utilizing the full multi-collision system.
We have time for a few questions.
Can you go back to slide 33? Yeah, thanks. So I've been seeing these like twist diagrams pop up a lot recently as a way to describe jet crunching actually in the medium, but to be honest, I'm a little bit confused about how to read them. So could you like explain maybe what the big blobs are supposed to be?
My experiment is understanding is
Okay.
there's a cut diagram, you can correct me if I'm wrong. Cut diagram is, so you have a proton going in, you have another proton up here, and how I understand this is that you have a quark coming from one proton, quark coming from the other, you have photon going out instead, or photon, it's kind of complex scattering, right? And then you have, so in twist 2 you would have this, you don't have this, but in twist 3 you're interacting, so you're a final state gluon is interacting with the remnants of the photon.
Okay. I was missing that there was protons.
It's
That really
kind of
helps
hard
with that.
to read these diagrams as an experiment.
Okay. Thank you.
Yeah.
Thanks for the nice talk, and I found the measurement of JT versus fragmentation function at LHC very interesting. I was just wondering if that's unfolded.
It's that I've used the I think you're the one who is using the Omnifold, right? No?
Multiple, yeah.
Yeah, Omni. Let's see. So I've used Omnifold to unfold that.
Oh, cool.
Yeah.
Any other questions? If not, let's thank Sookhyun again for a great work.